everyone. We're going to be talking about exoplanets broadly today. And I guess I wanted to start off with who I am. Just like Ben said, I'm a PhD candidate at Ohio State, and I broadly study exoplanets. But more specifically, I look at planet demographics, and I end up asking this question a lot. When did the first planets form? And I kind of wanted to get a whole bunch of these pictures just stacked of the same slide and me just saying this a ton of times. But, we'll just have one here for now. But more specifically, what I mean when I say, when did the first planets form? I'm actually asking how much material is required for planet formation. So this is one of the questions that I look at in my research. And I also try to answer this question of how do planet populations correspond to different elements, which kind of is a cool thing that we can do at this point. And it's kind of something that we're just now able to start looking at. And on the other side of things, I also do planet interior models. So I basically look at how these different elements behave in these rocks and what we can learn about them. So a couple of questions that I think about are how volatiles, like CO2 and water, impact the observable properties that we see in these stars, or in these planets, like mass and radius, as well as density. And then another thing that I look at and consider is how planets evolve from this magma ocean phase and into different types of planet populations, like water worlds, lava worlds, all of these sorts of things, which these sound pretty in-depth, but we'll get to this later in the talk. So I want to start out with just defining what an exoplanet is. And so, like the title implies, an exoplanet is just a planet that is not within our solar system. So it's outside of our solar system. We can have free floating planets, and they do exist. So they don't have to have a star. But generally, we find them around stars, and we find them within our galaxy. So currently, we're not at the stage where we can look into another galaxy and see exoplanets, so if anyone tells you that they have discovered an exoplanet in another galaxy, be a little bit skeptical, because we're not quite at that point. So in general, the talk is going to cover 4 basic points, or not basic necessarily, but I'm going to cover 4 topics, and we're going to start off with detection methods. So I'm going to tell you guys how we actually find these sorts of planets. Then we're going to look at some planet demographics. So what type of planets we're actually finding around these different stars. And then we're going to move on to planet formation. So how are we getting these different types of planets, and how are they forming? And then we're going to wrap up with some questions about habitability and searching for life. So let's get into it. So detection methods, how do they work? So generally, there are 4 different detection methods that we astronomers use to actually find these and discover these exoplanets. And the way that I've rated these and the way that they're going to come up is from most detected planets to least detected planets. So the method that we have that detects the most amount of planets, and the one that I personally use, is the transit method. So what you'll see in this GIF is this planet orbiting around its host star. And you'll see a plot on the bottom where you have brightness as a function of time. And so what we do is we point our telescopes at a particular star, and we measure its brightness as a function of time. And you'll notice that there are these 2 dips when the planet orbits in front of its host star. And then there's a dip that we see when the planet is behind its host star. So this is what we call the transit. And the depth and the depth of the transit corresponds to how large the planet actually is. So when we're thinking about an Earth-like planet or a really small planet, it's going to make less of a dip in this light curve. And we call these brightness versus time plots a light curve. We'll see a smaller dip than if a Jupiter-sized planet orbited in front of its star, and it would be a much deeper dip. And so when the planet goes behind its host star, this is called an occultation dip, this short one that you're seeing here. And generally, unless the planet is super, super hot and super bright, we don't actually get to see this occultation dip that often. So what have we found with the transit method? So this is just a plot of planet mass as a function of semi-major axis. So the semi-major axis is basically how far away from the host star the planet is. And to give you some context and into what these numbers are, on the x-axis, 1 is where Earth is, and on the y-axis, 1 is also where Earth is. So 1 kind of falls in this intersection of those two numbers. So you'll notice that we're able to see a lot of stuff that's pretty close to its star, actually closer than, most of the planets that we're finding are closer in than we are to our sun. And we find them mostly clumped together aside from this little section here, or this little triangle area that we call the Neptune desert. And so we're trying to actively figure out why aren't any planets here. So one of the current ideas for why this weird gap is here is that basically you have this might be a transition state and it's not stable for planets to remain in. So they might end up losing a lot of their atmosphere. So this is one of the current theories as to why there's this Neptune desert. And so since I don't get to show my data plots very often, I had to throw this up here. So this is what real data looks like from a real telescope. So this is some data that I've currently been using from TESS, or the Transiting Exoplanet Survey satellite, and it looks like this. It's kind of a goofy looking thing, as most of the telescopes are. And what you'll see in the top plot is this function, this plot similar to what I showed you in the GIF of the brightness or the flux as a function of time. And you'll notice that there are these lines that have dips. And this is just showing you where the data points are for the transits that we're seeing here in the data. And so what we end up doing is we end up folding this light curve and basically stacking all of these dips that we find on top of each other. In this case, we had about 4 or 5 dips. And so I stacked them all on top of each other, and this increases the signal to noise, or the statistical significance of the detection. And so you'll end up seeing, so in the middle plot, you see it all stacked, and then the bottom plot's just a zoom in of this planet. And so, like I said, this is a planet candidate. So we're following up observations on this planet candidate to confirm whether or not it actually is a planet. And fingers crossed, it is, because it would be the first planet that I have discovered after 4 years of trying to find a planet. So it's not easy. And I want to shout out to another telescope that one of the first transit missions, the Kepler mission. And this telescope looks kind of like a lipstick tube, but this was basically what we had been using before TESS launched to detect planets, and it found thousands of planets, and really kind of set off this whole field of really being able to do a lot of statistics with a large population of planets. So the next detection method is radial velocities, and this is kind of like the Voldemort of detection methods, at least for me. So if you are a transit person, you basically well, you might like radial velocities, but most people in the field, you're either a transit method person or you're a radial velocity method person. And yeah, so I definitely fall into the transit methods. But here, what we're looking at is something quite different. So you'll see this planet orbiting around its host star, but you'll also see the host star getting shifted around as well due to the planet. And so this is just an interaction between masses and, the center of gravity for this thing. And so, basically when this happens, you end up getting, because this planet or because the star is moving basically forward and backwards with respect to us, we end up seeing the color of the star change. So as you'll see, as it moves backwards, it's more red to us. And as it ends up moving forward towards us, the star looks bluer. And we're able to use these changes in color or the Doppler shift or redshift to figure out the mass of the planet or the mass of the object that is disturbing this planet. And that's the radial velocity method. And this actually came predominantly before the transit method. So the radial velocity method has been able to detect quite a lot of planets. But as you can imagine, it is also limited to certain things. So you might notice that on this mass and orbital period plot here of the planets that we've detected, we haven't really detected any planets that are super small, around 1 Earth mass. They're generally much higher mass. So it does a better job at finding these high mass planets that are further away from their host star. And that brings us to the next detection method, which is microlensing. So microlensing is kind of a wild and crazy detection method. It's pretty fun. So what this does is it's basically using how light bends and using gravity as a magnifying glass. So it's basically gravitational lensing. So what will happen is you'll see a planet and its host star moving behind a particular light source. So right here, it's a star. And if you're observing the star in the foreground, its brightness will be basically maintained, and then you'll get this hump as the star comes in and is magnified behind the foreground star. And so that's what this larger hump is. And then the planet, there's a planet around this star, you'll end up seeing these spikes. So these 2 spikes are actually the planet that you end up seeing. And this method's kind of interesting because it's a one and done sort of thing. So if we detect a planet this way, we can't reobserve it. So that's kind of one of the cons of this method. But generally, it's a pretty good and robust method for finding exoplanets, particularly for planets that are further out, as you'll see on this plot again. So once again, this probes a different parameter space. So it predominantly looks at, once again, further out planets, and it's not super mass limited. So it can get down to these lower mass planets, but the current telescopes that we have just aren't that precise yet. There's a telescope that's coming out pretty soon called Roman, and it should be able to probe basically that Earth mass, right around that Earth mass region really, really well. So we're able to find a decent bit of planets this way. And then the last method that I'm going to talk about is direct imaging. So this is where we actually get to see the planet. And so the GIF on your left is these dots that are rotating around this star, this yellow star in the center of the GIF, are actual planets orbiting around their host star, which is pretty cool. And so what this looks like is, if you look at the image on your right, you'll notice that there's a telescope and it's pointing towards this thing right here, which is called a coronagraph. So that's the same thing that you'll see here on the GIF, basically that blocked out portion. And what this is basically this coronagraph blocks out the light from the host star so that we can see the exoplanets, which are much fainter. And it's kind of similar to, if you're at the beach or something and you're trying to see, maybe someone that's really far out in the ocean or something, you cover your eyes and so you can see them much better that way. So it works similar to that. And so going back to this coronagraph, you'll notice that it's also shaped kind of like a flower. And what this does is it's actually a lot better than just having a round circle. And what it does is it helps diffuse the light a lot better from the host star so that you don't get these aberrations when you're taking observations of a star. So that's what that does. Although it does kind of look like some Lovecraftian horror sort of thing. So with direct imaging, we actually haven't detected that many planets because it's really, the observations are really expensive, both time and money expensive to do. So we generally look at already detected planets with direct imaging, but sometimes we do end up finding actual planets themselves. So these are limited to higher mass planets, and this is mostly because when a planet is higher mass, they're most likely going to be a little bit hotter, and specifically they'll be hotter because direct imaging predominantly looks at newly forming systems. So very young systems, which are just generally hotter than a system like our solar system, where everything's kind of calmed down and cooled down a bit. So putting this all together, you'll see that we probe a decent bit of this parameter space, but we've got a lot to look at in the future. So all of these dark regions, which some of them will be addressed with future missions, and some, we're still in the planning phases of trying to figure out how do we look at this region of this parameter space. And just to throw up a couple of planets that are in our solar system to give you some context of what we're able to look at, we've got Earth here down at the bottom. So currently, we're not able to probe this region too well, or at least not as well as we would like. Then we have a Jupiter planet. So we are able to actually detect these sorts of planets. However, Jupiter is basically on the very edge of what we would be able to detect at this point. And then last, we've got Neptune, which a planet that far out at that low mass, currently we just don't have the ability to look at this, but hopefully in the future we'll be able to look at that. And speaking of different planet types, there are actually a lot of different planet types. And I love this graphic because it kind of goes into a whole bunch of different ones. So going from biggest to smallest, we've got the gas giants. So think Jupiters and Saturns. So these are predominantly, made of gas. And so they generally have an iron core, an iron and rocky core. And so the next smallest is Neptune-like planets. So these are also these are a decent bit smaller than the Jupiters and Saturns. And they predominantly have atmospheres of hydrogen and helium. And then we also have basically this thing that we call mini Neptunes or sub-Neptunes, and they're just slightly smaller than the Neptune sort of planets. Then we have super Earths, which are where we're getting into this rocky composition. So these are more rock than they are atmosphere at this point. So this is anything that is smaller than a mini Neptune, but larger than Earth. And then lastly, we get to these Earth-sized planets that are once again rocky. And they end up being planets that could or could not have atmospheres because of how small they are. So looking at kind of plotting all of these types of planets on a graph, what you're looking at is the number of planets that we've detected so far versus the planet type. And we've got a couple of different planets from our solar system on here to represent what we're looking at. So what you'll notice is that there are two big spikes in the middle. So looking at these, as well as the super Jupiter-sized planet, we don't actually have any solar system analogs for these, which is really interesting and makes considering what's going on these planets and what could potentially be happening either on their surfaces or within the planet itself, quite an interesting challenge to address. So and so all of these types of planets form different ways. They have different formation mechanisms. So that's what we're going to get into now. So I'm going to bring up this periodic table. And if we want to build a planet, like a no-frill sort of planet, you basically have, the lowest model that you can get of a planet. You need a couple of different elements. So you would need to have a core. So you would want iron for your core. And then you would want some sort of rocky elements. So we have predominantly magnesium and silicon, but you could throw a little bit of calcium in there and maybe some oxygen. And those would be very good things to want. And then if you want an atmosphere, at the bare minimum, you need a little bit of hydrogen and helium. And once again, this is a bare bones planet. So if you look at this periodic table, Earth has all the frills. It has all the options that you could have. But this is just your basic model. So in order to build this planet, we couldn't exactly build it once the universe started, because at the beginning, we only had hydrogen, helium, lithium, not to mention everything was kind of a gas. So it was not in peak planet forming configuration. But if we pass about 100 million years or so, we start to get some other elements that would be planet forming elements. And so even though right now we have enough for a no frills sort of planet, this probably still wouldn't be a good point at which we could make a planet itself, because we would need enough of the stuff to build a planet. So, for example, if we only have, we may have iron at this point, but how much iron do we have? Do we have, like a rock, like a small boulder size amount of iron? If so, we wouldn't be building a planet out of that. So if you pass another 200 million years, you get all of these elements, which it's getting close to being around Earth-like. But for sure, after 8 million years, we have all the things that we need to actually build a planet. And so what you'll notice here are that there are different types of, there are different colors on these different elements. And so they correspond to the fraction that makes up that planet. So, for example, iron is the iron that we have in our universe predominantly comes from exploding white dwarfs. And then it also comes from exploding massive stars. So in the beginning, it was predominantly green. Now it is predominantly blue after these white dwarfs start exploding. So at this point, we would be able to actually build a planet theoretically if we have enough of these materials. And so just throwing this back up on the screen of the elements that we need to actually build a planet, you'll notice that that basically we have all of them, and we have all of them from basically all of their sources at this point. And we've known for a while, actually, from the first 4 planets that were ever discovered. They were giant planets. And basically, I think that around in 2000, we had 4 of them. So people started trying to do planet demographics with basically 4 planets, trying to figure out what we could find. And we found that there was a strong correlation with iron for these gas giant planets. And so we call iron, this trend with iron, well, we call iron specifically in astronomy metallicity. And so we have this metallicity trend. So let's break down this plot before I continue on. So on the y-axis, we have a planet occurrence rate, specifically giant planet occurrence rates here. And what this is it's just the percent of stars that are predicted to be that are predicted to host a particular type of planet. So, for example, if I were to say the planet occurrence rate for Jupiter's is 1%, then that would mean 1% of the stars in 1% of the stars in our galaxy would host Jupiter type planets. And then this x-axis looks at this metallicity. And so we call this Fe on H, so iron to hydrogen ratio. And so what this really is saying is the amount of iron within a star compared to our sun. So 0 on this plot on the x-axis is our sun. That's exactly where our sun would sit. So anything that is negative or less than 0 has less iron than our sun. And anything that is greater than that has more. And so to put this into context, the scale is actually log scale. That's what the brackets are showing here. And so a -1 metallicity or iron to hydrogen ratio is about 1 Earth mass of raw material when a planet is trying to form. So at the minimum, you could not build a planet greater than this amount, than this mass. So going back to this plot, from, like I said, the first 4 planets that we ever discovered, we found this trend. And so one interesting thing to note here is that they were limited to data of up to -0.5 metallicity. So these works started trying to constrain this function of metallicity, the planet occurrence rate to metallicity. And since they were only limited to this data, this spurred on several different works trying to constrain what's going on here for planets in this regime. And I even looked at planet occurrence rates for these really metal poor or low metallicity stars. And other works have also looked at this compared to by different planet types. So you'll notice that some planets like the Jupiters and sub-Saturns, they have a steeper slope, which means that they care a bit more about whether or not you have enough iron to build them. And the super Earths and sub-Neptunes have a bit less of a trend or care a bit less about how much iron is there. This is most likely due to the fact that they require a little bit less of the material. So you would really need to look at these lower metallicities or lower amounts of metals to really see this area in which they really start to care about the amount of iron within the system. And that's actually some of the stuff that I do. One of the papers that I'm about to publish actually kind of looks at this really metal poor regime. So basically, once we get these materials, how do they form? So I'll start off with terrestrial planet formation, and I'll touch a little bit on how gas giants are formed. But basically, you start off with this protoplanetary disk. So when your star is forming, it has a whole bunch of gas around it, which is what we call this protoplanetary disk. And it's made up of a whole bunch of dust particles, just like dust in your house. And so what happens is, as this protoplanetary disk is moving around and churning, these dust particles will start to clump together and they'll begin to form tiny rocks. And then they'll eventually form planetesimals, which are these kilometer-sized rocks. And then these rocks will end up hitting each other until they get to become planet embryos, which are a bit larger rocks. until these guys will end up hitting each other, which is where we get these giant impacts from. And once everything's said and done, and after all of these giant impacts, you'll end up with this terrestrial planet, and it will be a molten planet. It will be hot, super, super hot from all of these impacts, hot enough to make the whole planet molten. So that's where this idea of a magma ocean phase comes in. So you'll form these planets. They'll go through this magma ocean phase. Even Earth went through a magma ocean phase until it eventually cools down. And depending on what materials it starts out with, then you'll end up with different sorts of terrestrial type planets. But looking at this plot of basically time and the amount of stuff that you have to build your planet, we get this plot, and you'll see that there are two different pathways, one in blue and one in red. So like I said, all planets start from this protoplanetary disk. So you'll see this dust coagulation portion. And then after that, they end up splitting off. So for the terrestrial planets, like I said, you'll go through this planetesimal phase, giant impacts, until you get to your actual terrestrial planet. But for gas giants, they're typically thought to form beyond this snow line. And so within this protoplanetary disk, as you can imagine, as you move further and further away from the host star, you end up getting cooler. So there's a point at which it's cool enough to where you can actually form ice. And that's where these Jupiter-sized planets are thought to form really far out from their star. And what happens here is that you end up getting this accretion of these pebble-sized objects, so centimeter or so sized objects of ice and, rocky materials. And then you end up getting basically enough of it to where you get what we call runaway gas accretion, where you just start sucking in basically everything. And then you end up getting this really, really massive planet like Jupiter or Saturn. And that's typically how we think that these planets form. And so from this, we end up getting these really cool emerging planet populations depending on their initial conditions in which these planets form. So I'm going to specifically talk about terrestrial planets here, but there are a lot of different types of giant planets like hot Jupiters that are really close into their star and whatnot. So this is just going to give you a taste of the terrestrial side of things. So for this, we end up having lava worlds. So these planets are super, super hot, close into their host star, and they have they're basically on orbits of probably less than 10 days or so, and meaning that they really do travel around their star in 10 days. And so because of that, their surface is molten, and that's hence the name lava world. But also they don't have any atmosphere because the radiation from the host star ends up blowing away the atmosphere for these planets. And there are some people and some theories that suggest that they may have a rock vapor atmosphere, meaning that it could be so hot that it basically vaporizes the day side of the planet, and you end up getting a very slight atmosphere because of this vaporization as the rock's basically getting disintegrated as away from the planet. So most likely these planets are going to be disintegrated completely at some point. And then we have water worlds. So water worlds, you would need to most likely form outside of this ice line that I talked about. And if you formed outside of this ice line, then you could basically accrete enough water in frozen form. And if you migrate the planet in, if you migrate the planet in, then this water would just melt and you would end up with a water world. So if you ended up in some sort of zone where it was warm enough for that. So that's where we would get these water world sort of planets. And then we also have desert planets. And so these are planets that most likely formed inside of this snow line. And so they didn't get enough water onto them or ice onto them. And so, they're basically just dry, and they can or cannot have atmosphere similar to water worlds. So think of something like Mars. That would be a great definition of a desert planet. And then lastly, we have Earth-like planets. So these Earth-like planets, as the name implies, they have enough water where they're not completely a desert planet, but they don't have so much water where the whole surface of them is a water world. And generally, they should be of a nice climate and whatnot. So basically just think similar to Earth. So with this knowledge, I want to ask you guys a question, because I always find it really interesting what people say. But what do you think is the most common type of terrestrial planet that we've discovered to date? And so definitely take a couple of seconds and look at this. And yeah, so I'll give you a couple of seconds to see what's happening. Okay. I'm seeing some D's. Okay. So if you answered lava worlds or desert planets, I would give you an A. Not that any planet, I feel like this isn't an obvious answer, because I feel like a lot of the times in media we see either water worlds or someone talking about Earth-like planets. And so we end up seeing a lot of lava worlds and desert planets, and this is mostly due to the way that we're detecting these planets. So if you'll notice in this bottom region here, the way that we detect most of our planets that are Earth-like or terrestrial type planets, they're actually it's with the transit method predominantly, which means that it's mostly close-in planets. So that's why you end up getting these really hot or desert-like planets. Not that we haven't detected water worlds, we 100% have, but most of them so far are these lava planets or these desert planets. Which, speaking of the types of planets that we're discovering, this brings me straight into this idea of habitability and Eta Earth. So what exactly is Eta Earth? So this Eta Earth is what we define to be an Earth-like planet in habitable zones around sun-like stars. And we'll break this down a little bit, but we know what Earth-like planets are. But I want to look at this habitable zone thing in more depth. So in terms of a habitable zone, when we're thinking about this, we want something where we can have water. So on this plot, you'll see this bottom image that has the inner solar system. And this area right here in green is what we would consider our habitable zone. So anything inside of that or that's not in this green would not be in the habitable zone. So for example, Venus, it's right on the cusp of being in the habitable zone. It might teeter on the edge, but we know that Venus isn't habitable because it has greenhouse gases. And similar to Mars, Mars is also kind of on the cusp or on the edge of this habitable zone. And once again, it's a dry desert planet. So this is what we're thinking about here, but the habitable zone depends on the type of planet. Sorry, it depends on the type of star. So, for example, looking at the top, we see this system called the TRAPPIST-1 system. And if you can kind of see it, it says enlarged. So this whole system would fit inside of where Mercury is. So it's very, very close together. And it's around a star that is extremely small. And so this, even though there are a whole bunch of planets within this habitable zone on this plot, they would not be considered A to Earth because they are not an Earth-like planet in a habitable zone around a sun-like star. But this is one of the systems that people are looking at with JWST, this new telescope that we have out, to kind of look and see if there could be life on these planets. So aside from being in the habitable zone, if we're thinking about planet habitability, we would want to think about what's happening on the surface of the planet as well. Particularly, we would want to think about tectonics or plate tectonics. And we have two regimes for tectonics. So we have plate tectonics, which is what we have on Earth, which is basically this mixing of the planet's crust with the mantle. So, anywhere, basically, most of the places where we have earthquakes or volcanoes, those sorts of places end up having basically this mixing of the mantle and the crust. So a lot of stuff going underneath, and some stuff actually coming up, through volcanoes and whatnot. But most of the planets that we found are in this stagnant lid regime that I'm showing you here, where basically you've got this crust of the planet and it doesn't interact at all with the mantle. The mantle's doing its own thing. So just to show you a plot here, you'll see that Earth kind of sits on this line where it almost could have been a stagnant lid sort of planet, but we actually end up having a lot of plate tectonic. Well, we know that we have plate tectonics here. And so, but other planets in our solar system, we know are stagnant lids like Venus and Mars. And that's probably one of the reasons that Venus actually is a greenhouse gas planet. And specifically, this is because what plate tectonics do is very important, and it basically makes us have this CO2 cycle, which you may have heard of. So what the idea of this is that we have CO2 in the atmosphere, and then it gets rained down into our oceans. And then from the oceans, it gets subducted underneath into the mantle through these plates. And it ends up staying under there for quite a while, which helps remove some of this CO2 from our atmosphere so we don't end up becoming this greenhouse gas sort of planet. And eventually it'll get re-emitted from a volcano or whatnot. But this works to regulate our atmosphere. And so one of the things that we look for when we're thinking about habitability and wanting to actually detect habitable planets is looking at these atmospheres for biosignatures. So biosignatures are basically looking at the planet's atmosphere to see any sort of traces of life. And specifically, when we're thinking about what we want as a biosignature, we want it to have at least these few things. So we want it not to exist naturally within the atmosphere at ambient temperatures and pressures. So, things like hydrogen or water. We also want it to be not created by geophysical processes. So things like CO2 are created by volcanoes, so we know that wouldn't be a good biosignature. We want it to have a strong spectral feature, and I'll get into what this means in a second. And then lastly, we don't want it to be created or destroyed by any sort of photochemistry happening in the atmosphere. So this means just anything going on by, photochemistry. So anything happening with the sun that could destroy it. So thinking about this spectral feature, what a spectrum is basically the amount of light that is absorbed by a particular molecule. And so what you'll see here is basically these different molecules absorbing different wavelengths of light. So different molecules absorb a particular wavelength of light that is unique to them. And so this is the way that we're able to figure out what is exactly in a planet's atmosphere. And basically the star lights up the planet, and then we observe it, and then we're able to get these really cool spectra where we're able to see all of these different molecules. So you'll see carbon dioxide here is a very strong feature, meaning that you notice that the dip is really, really deep. So it should have a strong signal here. Whereas something like, water is a bit harder to see. And if you were an astute alien, you would notice that we have molecular oxygen, which for Earth would be a biosignature. So if you were looking at Earth as an alien, I guess we would be the aliens at that point. But then molecular oxygen would be a great biosignature for us. However, the issue with molecular oxygen for us specifically is that currently we're not able to detect it with our instruments that we have now. So definitely advances in instruments would help us detect molecular oxygen. So, but in general, if you think about oxygen in general, is it a good biosignature? So the long story short is that oxygen can be made in atmospheres that for super Earths, which are what we're predominantly looking at, as well as mini Neptunes, it can be made in their atmosphere from a variety of initial conditions. So, like I mentioned before, we start off with this magma ocean planet, and then if it ends up having more carbon to hydrogen, you can end up with a runaway greenhouse gas planet that also has oxygen in the atmosphere. So that would not be good there. And then we also have, if it has too much water, you can end up with a water world, which in theory you would think would be a good thing. We could probably find life on that, but you end up with oxygen in the atmosphere as well from just having a lot of water. Same with having too little water. You can also end up with a lot of oxygen in the atmosphere. So oxygen is not necessarily the best biosignature for super Earths or mini Neptunes right now. So what is? So for super Earths, a lot of the research is surrounding methane. So a lot of people think that methane is what you would want to look for if you were looking for some sort of biosignature on these planets. And then for mini Neptunes, you would want to look for ammonia. So both of these things are currently actually being looked at with JWST. And so JWST is actually, looking at quite a few super Earths and mini Neptunes just for this. So so this is basically the end of the talk. I did want to kind of advertise an astronomy podcast. So if you're interested in space stuff, me as well as 3 other grad students, we talk about, current research going on at, an accessible level. It's aimed towards like undergrads and the public. So if that's interesting to you, definitely check that out because it's a lot of fun to record, but also, it might be interesting to you. And with that, thank you so much. And I am, of course, happy to take any questions.
Fantastic. So we'll just jump straight into the questions. Let's see. This would help if you could hear me.
I can hear you.
Oh, you can. Okay, good. All right. Uh, is data collected from multiple gathering times? So this was during the transit um, data that you showed. Do you collect the data from multiple times, and if so, how do you ensure that you're looking at the same planetary body?
Yeah, so we do. Um, yeah, that's actually really interesting because a lot of the stuff that we do is calibrating these telescopes, which isn't something that I do generally,
Okay.
but the idea is that we have what we call RA or right ascension and declination. And these are basically coordinate systems to get us to the exact star. And it's this agreed upon system with respect to, kind of where we are. And we call it the galactic plane.
Okay.
So yeah, we do that, and that's where our calibrations come from, and we do look back at the same places.
Okay. That's really cool.
Hmm.
Is the assumption for finding exoplanets that they're close to Earth mass, they have much larger or smaller mass, and still be habitable?
Yeah, so the in terms of habitability, they can a lot of the people are thinking about the larger masses as opposed to smaller masses. One of the reasons why people don't think about smaller mass planets is because at a certain point, you actually aren't massive enough to hold on to an atmosphere. So, for example, Mars doesn't really have much of an atmosphere. And so, when we're thinking about habitability, we don't tend to think about these low mass planets for that reason, but also because generally they're very hard to detect, at least where we're at currently. And then on the other side of things, I think that at least up to mini Neptunes is where people are looking for habitable planets.
Makes sense. Let's see. How is the coronagraph designed to be optimized?
Oh, that's a great question. So I'm actually not 100% sure on this because I haven't actually done a lot of instrumentation exactly,
Okay.
but I do know that when when you're doing the coronagraph, it at least needs to be large enough. So it has to do with how far the stars are that you're looking at, of
Okay.
course. And so you would want it to be large enough so that it would block the close in stars light, as
Mm-hmm.
well as you would need to be able to pull basically your telescope far enough away to where it would still block the light for further away stars as well. So
Okay.
I'm not exactly sure how they come up with a number, but
Yeah.
those are at least the parameters that they're looking at.
Okay, that makes sense. So, yeah, I mean, it all seems very complicated, but yeah, it's a really neat technique, though.
Yeah.
Sure. Let's see. Do the planets tend to switch from one type to another over time?
Yes. So I didn't bring it up here,
Mhm.
but the there's this idea and there's this thing that we call a radius gap
Okay.
where we see this dip between these super Earth planets and these mini Neptune planets.
Mm-hmm.
And one of the ideas is that as they evolve, some of them will lose their atmospheres and
Mm-hmm.
they'll end up becoming a super Earth instead because they've lost a ton of gas due to it could be their star or um, you know various processes. Maybe it's just not massive enough to completely hold on to it with what
Okay.
it started out with, and
Yeah.
then it just loses it. So yeah, 100%.
Interesting. Okay. Let's see. You may have talked about this, but I'll go ahead and ask in case you. Is there a good explanation for the correlation between metallicity and occurrence rates?
Yeah, so the idea here is that you need enough stuff to build your planet.
Mm-hmm.
So um the idea is that if you have more of the stuff, you should, in theory, be able to make more of the planets. And we do see this for up to a certain point for these, for most planet types. And actually, you end up plateauing at some point for super Earths and sub Neptunes. But that's the basic idea, is that we use metallicity as a proxy for the amount of material that's available at the time that the planet is forming.
Okay, I got you. Given the right technology, would it be possible to convert a desert planet to a more habitable planet like Earth? Fuel cells produce water that is then just put out on the.
So I think that you probably, okay. So I feel like this is getting into the weeds.
Oh yeah.
But I think that you actually, if so, just because a planet is a desert planet doesn't mean that it doesn't have water locked inside its mantle. Actually, there are a lot of ideas that, and even for Earth, there's a lot of actual water that's locked into the mantle of the planet. So, I mean, yeah, I feel like if you could somehow pull that water up 100%, I don't know how you would do that. I
Sure.
feel like
Yeah.
that would be like such an engineering feat. But yeah, in theory, you could.
Okay. That's interesting. In the TRAPPIST-1 system, does having the planets so close together affect how gravity is felt on the planets?
So I don't think that it would, because just like it would in the sense that the orbits would be, the orbits are also feel a bit of the other planets, similar to how we orbit. We also feel a bit from Mars as well as Venus as well as Jupiter. But it doesn't actually impact if while we're on Earth, we don't actually feel any sort of difference in terms of the path we're following, because they're both the planets, if they're in an orbit that's stable,
Yeah.
it's just basically going to be continually going, and you wouldn't notice it at all.
Okay. Yeah, that makes sense. How do you detect the type of regime of a planet? Mind blowing to be able to do that from.
So I don't know if the question in terms of the regime is the maybe plate tectonics. But yeah, so in terms of the plate tectonics, it's actually really cool. A lot of we're not actually able to detect any sort of plate tectonics itself on the planet just yet, but being able to actually look at the like with JWST, we'll actually be able to kind of probe what's going on in terms of whether or not the planet has a substantial atmosphere, which basically we can infer whether or not the planet would potentially have plate tectonics. So it's more inference at this point than actually seeing the planet. And that's where a lot of these planet interior models come in. And so you can infer these things by like a lot of different things like mass, radius, temperature, and then a whole slew of information about the elements that are actually on the planet from spectroscopy. So it's more inference, but it would be so cool to actually see it one day.
Oh, absolutely. And the person to ask confirmed that they were asking about the plate tectonic. Good.
Okay,
Yeah,
cool.
nicely done. I guess I just along those lines. So you mentioned there's the plate tectonic, the planets that have plate tectonics, and then the ones that have the sort of fixed mantle. Are you able to tell anything about what's under the mantle that don't have tectonics?
Yeah. So what we end up doing is, once again, a lot of this is inferred
Mm-hmm.
due to the mass, radius, density, surface gravity, those sorts of things.
Mm-hmm.
But we can tell whether or not a planet is a Mercury-like planet where it's made of predominantly iron.
Okay.
So Mercury is made up of 70% iron, and we know this from the density of it.
Okay.
But we could also go to Mercury, which is kind of cool because it's in our own solar system.
Yeah.
But yeah, we basically get these measurements, and then we are able to figure out how much of each of these large sorts of materials, like I said, iron, as well as these rock materials, how much of it could be on these planets, as well as another way that we infer this is by looking at the host star.
Mm-hmm.
So the host star, similar to how it has the amount, similar to how looking at it tells us the amount of iron that was there in the protoplanetary disk when the planet was forming.
Mm-hmm.
We can look at other elements like rock forming elements to figure out how much of that is available as well. And we are able to tune our models to kind of see what sort of planets that we're getting and if it lines up with the observations of the planets themselves in terms of the density and whatnot. So, yeah.
Okay. Oh, that's really cool. That's really neat. Let's see. So I think so. Unless we get any more questions in at the last minute, I think this will be our last one. But it's a good one. Why is it hard to detect molecular oxygen? What advances are conceptual or technical?
So it's technical limitations for sure. So let me go back because I think that this will probably be better to show with the actual thing. So can you see my mouse?
Yes.
Okay. So what we're looking at here, similar to how I mentioned the transit, how you end up getting deeper lines. So like carbon dioxide, for example, is pretty deep here. So you're able to actually see this a bit more easily. So basically, if we can get a better telescope that will allow us, that has less noise, because a lot of the time, similar to that transit that I showed you before, we have a lot of noise in these observations. So really what you would see is a whole bunch of basically lines going up like this,
Mm-hmm.
which could mask these smaller features. So that's why it wouldn't be super good for, I mean, molecular oxygen is a great biosignature for Earth-sized planets, 100%. But we need to have better telescopes, which means better optics, which means, we need more engineers. So, so it's basically technical, but I'm pretty sure that we'll be able to do this, maybe not super soon, but I feel like within the next, 20 or 30 years, we should have way better precision of telescopes. Even with JWST, we're finally able to start seeing, features like, methane. The issue, but this is specifically for super Earths, which are larger, which means that they're a little bit easier to see in general. So that's kind of the difference there.
Okay. So basically, like as we advance the technology, we should be able to start making these detections.
Yeah, basically. Yeah.
Okay.
So fingers crossed, maybe I'll be eating my words in 30 years and hopefully no one remembers that I said this, but fingers crossed in 30 years we might be able to see molecular
Hey, you
oxygen.
know what? I believe. I think we can make it happen. All right. Well, thank you again for a fantastic talk. Thank you to everybody that came out and asked questions. This was super cool to learn about. I knew next to nothing about it, and I feel much more educated now. So I really appreciate you sharing your work and also explaining the field as well. So this was super cool to learn about.
Yeah. I'm always happy to talk about science.
Good, good. I mean, you can tell it was really entertaining, but also very informative. All right.
Awesome.
So if I can get you to hang around for just 1 second, we'll talk very briefly. For everybody else, thank you for coming out. We will be back next week. I think 5 talks in a row scheduled right now. We will get more as well. But we'll see you here next week, same time, same place. Have a great weekend, everybody.